Okay, so we're back for FamilyMath182b, and this is a theorem. These two theorems I learned about in Coxeter-Greitzer's Geometry Revisited, which is just an absolutely amazing book of geometry. So these are the first two really advanced theorems in geometry that you've ever seen. And don't worry, I'm not going to prove them, because it's a little involved. I could actually walk you through it, or at least the proof of this one. But I just want you to see them and just show you some really neat things in geometry. So that problem, that challenge problem this morning, reminded me of this theorem. And these two theorems say this: take any triangle, ABC. And I meant to make ABC the same triangle here. Okay. And instead of putting squares on it, put equilateral triangles on it, on the sides. Okay, so here's an equilateral triangle. Here's an equilateral triangle that has that side. And an equilateral triangle with that side length. Now notice all the side lengths are different. It doesn't have to be perfect symmetry in this one, like there was in the problem we did. And then it says just take the centers of the equilateral triangles and connect them up. What do you notice about the new connected up triangle?
Well, it looks like it could be equilateral.
Looks like it could be equilateral. Pretty neat, right?
Yeah.
Let's go over here. Instead of putting the equilateral triangles on the outside, now I put them on the inside. So you can see I have an equilateral triangle here. You see that? Off of
yeah.
AC. And then for AB it goes up here. And then for BC it goes over here. And I connect up the centers again.
That looks equilateral too.
Also looks equilateral. These two triangles, this one's called the outer Napoleon triangle. This one's called the inner Napoleon triangle. Have you ever heard the name Napoleon before?
Yep.
Where?
He was the guy who conquered Europe.
Yeah. So the legend is, and I don't know if anyone knows this is true or not true, but the legend is he was also a very good mathematician. And this theorem that says this is an equilateral triangle when you connect up the centers is named after him, because supposedly he discovered it. And this one too on the inside, supposedly he discovered that those are equilateral triangles. It's pretty cool. So Napoleon has this geometry theorem named after him. And this, like I said, it's not super hard, but it's a little advanced. But, so you put equilateral triangles on the side, connect up the centers, and you get another equilateral triangle. And it's any triangle. ABC can be anything. It doesn't have to be an equilateral triangle, it doesn't have to be anything. Any triangle this works for. Pretty neat, right?
Yeah.
And the same thing on the inside. If you flip them over and put the equilateral triangles in the other place, they're on the inside. And you want to hear something else that's incredible?
What?
If you look at the area of this Napoleon triangle, we'll call this Napoleon 1, the outer Napoleon triangle, and subtract the area of the inner Napoleon triangle, you get the area of triangle A, B, C.
Whoa.
The difference between this area, the big equilateral triangle, and the smaller equilateral triangle is the area of the original triangle. This kind of thing is why geometry is so neat. Who would have ever thought this could be true? Pretty cool, right?
Yep.
You want to learn more stuff like this?
Yeah.
Okay. All right. Good job tonight, hon. Good job. Busy day, but good job.